Dinner, we can start finally. And as I mentioned in the first class, in this class, you need to check attendance by yourself via Blackboard's self-attendance check system. So please don't forget checking your attendance via Blackboard. Okay. Okay. So in the previous class, we learned why we need to learn digital logic design. So, and then as I mentioned, I know that you are most of you are computer engineering or computer science students. Then so, I believe your interest in computer programming, how to make good software. But you know, as a computer engineering student, I mentioned that you need to understand every aspect of computer systems. And then digital logic design is a fundamental course for understanding the very complex computer system architecture. Okay, so I hope the through the first class you can understand why you need to learn this course. So I think the motivation is very important for students. Okay. So, and then also in this class, we will learn about the basic concept in computer systems, and then the basic concept in the digital system design. Okay, and then in the previous class, so in the previous class, I showed this figure. So as you can see, this figure shows the many layers in computer systems. And so most people think that if they handle the computer system, actually only the customers or normal people can be the back layer of the computer system, which means the application software. Okay, actually no, usually normal customers just see this highest layer of the computer systems, but in order to run this application software, so normal applications like the web browser, games, also machine learning applications, so like the ChatGPT. So actually, computer system requires these layers, so lower layers of the computer systems. So in order to run the application software, and you need to run operating systems such as Windows, Mac OS, or Linux. So usually, so recently the Linux is the very important operating system because the companies provide the machine learning application services via Linux operating systems. Okay? So I hope you can understand also how Linux operating system works in the computer systems. Also, architecture and microarchitecture. Actually, these are the part of the computer systems. So I believe everyone knows the software runs on the hardware. Okay, and then actually the performance and then every aspect of the software depends on the hardware systems of the computer systems. Okay, so that's why we need to learn about the hardware in the computer system, computer engineering department. So the microarchitecture and microarchitecture is part. Actually, this part handles some organizations in computer systems, and then usually the microarchitecture handles the inside of processors like a CPU or GPUs, and architecture part covers the entire organization of computer systems. And then in this class, we will learn about the logic and digital design, digital circuits. As you can see, the logic design, so you can find the adders and memories. And then I hope some of you understand the definition of adders and memories. Actually, the memory is very familiar word because everyone knows. I believe everyone knows about the DRAM or main memories of your devices, like the smartphone or laptop. So actually, we just check the size of main memories in your devices. Also, like adders. So actually, hardware, computer hardware runs based on the basic logic component, such as adders, multipliers, subtractors, something like that. So if you see that this word, then you can find the adder is the add plus er, right? So er means the unit or some worker that performs some functions. So and then this is the computer system. So actually you can understand this is the units of add operation. That's why this is called add. So computer systems just like calculators, right? So actually the first computer hardware is designed for accelerating arithmetic operations such as add, subtract, multiply, and divide. Okay, so actually computer systems are composed of many simple logic gates such as arithmetic units and memory units. So actually we use memories for storing our data, right? So computer hardware is composed based on the many basic digital component. And then actually under this layer, you can find the digital circuits. So actually these are the basic gates we will learn in this course. So we can build these adders, some arithmetic units using the basic logic gate. Actually, basic logic gates are very simple, so I believe everyone can understand easily about the operation of the basic logic gate. But based on these very simple logic gates, we can build somewhat complex. It's more complex, but it's also simple. Okay, we can build simple arithmetic units or basic hardware components. Okay, and then under this layer, actually these digital circuits are designed based on the theories in analog circuits, like the property or characteristics of CMOS transistors, or also some analog properties of basic circuits. Also, we can find the base knowledge on physics. Actually, the electric devices or some computers are based on the physics in electric physics, okay? Like the movement of electrons or some current voltages or something like that. So actually, the basic circuits are built on the knowledge in physics. Okay? So that's what we learned in the previous class. Okay, and then as I mentioned in this class, we will learn about the basic concepts of digital system design, and then basic concept of computer systems. It's a fundamental concept. Okay, so what is digital design? Then what are digital systems? So actually the definition of a digital system is very simple. If a system handles digital signals or digital data, then this system is called a digital system, right? It's very simple. So if a certain system handles the digital signals, then this is the digital system. And then the opposite term is the analog system, right? Then what are analog systems? It's very simple also. If a system handles analog signals, then this system is called an analog system, right? to understand what are these the signals and then what analog signals are. Okay. Then, so if you see that this slide, you can find that real world. So our real world is composed of analog systems. So what does that mean? Actually, the real signals and the real data we can observe in our real world are analog signals. So, for example, so you can find this is the figure of the sine wave in the circuit, and you can find that signals are continuously changed signal values. So in this figure, the y-axis represents the voltage level, right? So I hope everyone knows about the voltage of the electric circuit. But also this x-axis is the time. We can observe in this system the voltage level is periodically changed. But the voltage level is changed by time. And then as you can observe, these voltage levels are continuously changing. That is the property of analog signal. Okay? And then every data and every signal we can observe in our real world is analog signal, an analog signal, right? So if we use the smartphone, and we need to the smartphone communicates via some electromagnetic waves, like the 5 gigahertz waves, something like that. So actually, these waves are analog signals, right? So also, as you can see, you can find this is also so these are the concept of the electromagnetic wave. So as you can see, every values and then every level of signal is continuously. So analog means that it's the signal. So analog signal means some levels or values of a signal changed continuously by time. So continuously is the very fundamental term of the analog system. Okay? So analog system just handles these analog signals. So real signals, what real data we can observe in our real world. Then, what is the digital system? Then, what is the advantage of the analog system? Actually, we can observe the analog signals, which means that we can intuitively understand the analog signals because this is the real data and then real signals. Okay, so we can observe. It's a real world. Okay, so I just repeatedly say real because actually the analog systems handles the real world signals. Then what is the system? So as I mentioned, the systems handle the signals. So actually I repeatedly say analog handles the real data or real signals. Then how about the digital? It's the unreal data, and there's the unreal data. But we know every device is the most of every device, the modern devices are digital systems. So which means that our devices handle digital signals. Then we can just touch our devices, our electric devices, and then we know our electric devices are real devices. And we can watch, we can see the screens, also we can hear sounds from our devices. These are these are real signals, right? Then, what is what are these systems? I repeatedly say analog systems handle real data. Then these the systems handle unreal data. But it's not true because so when I mentioned about the analog system, then you need to understand, you need to focus on the terminology continuous signals. So handles the continuous signals, and then the real signals are continuously changed by time. So analog signal just handles the continuous data or continuous signals. Then what's the D0? D0 signals then handles the discrete signals. The opposite term of the continuous is the discrete. Okay? Which means that the signal values are not continuously changing. Okay, that is the signals. Actually, in this in the systems, the signals are represented as ones and zeros. Okay, that is the main feature of digital signals. So this is the analog signal, and as you can see, the values of the analog signal change it continuously, and then we can observe many continuous values, right? Like the if this is a 0, and then we can observe the 0.1, 0.2. But these are also discrete numbers, but we can observe continuous values in the analog system. And we can observe many values, many different values in the analog signal. But digital signals are represented as ones and zeros only. Then our analog signals, these signals, can be represented like the very discrete digital signals, such as this is the 1, this is 0, and something like 1, 0, 1, 0, something like that. Then, so we know our real signal is analog signal, but in order to handle these real analog signals, we use digital systems, which means our analog signals in our real world should be converted into digital signals if we want to use the digital signals using our digital devices. So which means these analog signals need to be represented, need to be translated into the digital signals, and then the digital systems handle these digital signals, right? And then the digital signals are represented as ones and zeros only. Okay. So what are the advantages of these signals? So in order to process these analog signals, and then I mentioned that the analog signals have many different values that continuously change it. So if there are many values, then we require complex systems. But actually, it's not easy. It's not easy to understand the analog signals, because analog signals have many values, many different values. Also, the analog signals are weak against the noises. So what are noises? irrelevant signals are added to our analog signals, and then these signals work as a noise signals. And then if signals include the noise signals, it's not easy to handle these signals. Okay? So, but digital signals include only ones and zeros. So digital signals are strong against noise signals. Okay, so something like that. If noise are included in these analog signals, then the waveform of the analog signals are changing. So in the digital signal, if these noises are included like this, but we can think that, oh, this signals is the 1 and this is the 0, 1 and 0, because there are only 2 values in the digital signal. That's why we use the digital system. Also, because the digital signals include only 1 and 1s and 0s, we do not require difficult mathematics. So you know the physics and mathematics are very difficult to understand, right? It's a very difficult subject. But if we just handle the 1s and 0s in our systems, then we don't require difficult mathematics. Okay, we just require discrete mathematics, right? But it's much easier than right. Some students do not agree with me. So actually, discrete mathematics is much easier than the real mathematics, right? So we don't require difficult mathematics subject in the computer systems, and then also we don't require the profound knowledge of physics. Physics are also difficult subject. So, and we have built systems using integrated circuits. So, you know, if you actually, so if you see the real CPU chip, right? Or if you just see some real DRAM beams, like in the desktop computer systems, then you can find that we can find many chips. It's called the chips, CPU chips or memory chips. And then we already know that these chips are based on the semiconductor technology, right? There is the chip for like this. It's a very old chip, old generation chip, for the old generation chip. But actually, these digital systems are based on the integrated circuits. We can build on the integrated circuits. So then what is the definition of integrated circuits? The definition is a group of many transistors. Okay, so we can build integrated circuits using many transistors, combining many transistors. So we just design allocate the many transistors in the circuit, and then just connect these transistors each other. Then we can build integrated circuits. So this slide shows the first integrated circuit, the photo of the first integrated circuit. So as you can see, so this is the first circuit, first IC. This is very simple, right? And then this is the first monolithic silicon IC. So monolithic silicon IC. The first is the first chip, first semiconductor chip by Fairchild component. So I believe you don't know about the Fairchild, but this is the very pioneering company of semiconductor industry. But maybe the Fairchild is purchase Intel later. So this is also the photo of the first monolithic silicon IC. So this transistor is manufactured using silicon, so semiconductor technology. So you can find the inputs like the input 1, input 2, and so you can find the output. No, the earth is a ground. So, and then also you can observe the connections. So these are metal lines. Okay? It's similar to the wire lines in our physical system. You can find the many metal lines, then also transistors here. Device only includes the one or two, a couple of those transistors. So this is the first circuit. It's a digital circuit. Okay. And actually, our digital systems are built on the integrated circuit. Okay, so many transistors, but the first circuit includes only a few transistors. It's a very simple circuit. So this is the photo of the some CMOS transistor layout. Okay, so I just want to show some simple design. So actually, in the early stage, so this IC design was very simple. So the circuit includes the several transistors. Okay, so the tens of transistors or hundreds of transistors. So you can find that the circuits are very simple. Circuits include several transistors. Okay? And then so we the early people drew the layout of this design the hand. The handwriting. You can find the handwriting here. Or you can also find the full layout of the IC design. And then actually the early stage of the semiconductor industry, these engineers do circuits like layers by hands, manually. Okay, so recently we use CAD tools like computer softwares to design ICs, the integrated circuits. But the early stage of the semiconductor industry, engineers just do this layout by hands. Then this is the first Intel 8088 chip. So you can find this photo, you can find many transistors. So there are many transistors in this layout. So if you compare the first transistor, this first IC includes the one or two transistors, but this Intel 8080 chip includes the many transistors. But we can find, this is rather simple compared to the modern integrated circuits. Okay, so you can find the here. So in this Intel 8080 chip launched in 76. Well, it's very simple. So all this IC design was relatively simple compared to the modern digital design. So this is the first Intel 8082. Okay. So launched in 1974, and then CPU frequency is 2 megahertz. And then recently, we use very fast CPUs, such as it works using 3 or 4 gigahertz clock frequency, right? But this is the first CPU made by Intel. So it used the CPU frequency of megahertz. It's very, very slow. So we will also learn about the clock signals in this course. And then technology node, 6 micrometer. So recently, so if you are interested in semiconductor industry, then you can know recently we are using under 10 nanometer technology, 10 nanometer. This technology node is the 6 micrometer. Okay, much larger than the modern technology. So which means that the size of a single transistor is much larger than the size of cent transistor, modern transistors. Because the technology node determines the size of a transistor, also the performance of a single transistor. It's very large, but 6 micrometer nano. And then you can find the number of transistors in this chip. It's 4,500, 4.5K. And then this is the dipole of Intel Xeon E7 is based on the Azure architecture. It's also this is not a older generation of the CPU. So recently we are using Ice Lake or some. So actually the server architecture is a little bit different from the customer CPU architecture. So actually the modern server CPU is based on the Ice Lake or enhanced Ice Lake architecture. But it's the Azure. This is the dipole. Okay, dipole of the Intel CPU, the modern CPU, and then you can compare some specification of the early stage CPU. So the die area is 662 kilomillimeter, and then also you can find the technology now, 22 nanometer. So and then I mentioned that recently we are using under 10 nanometer technology. So Samsung or TSMC are using 5 nanometer technology. And then Intel recently struggled for developing various enhanced technology. So Intel is also developing advanced technology, semiconductor technology. So just remember this number. This technology node size is smaller, then it means performance of a single transistor is higher, which means it's a better transistor. So its technology node is the 22 nanometer. It's much smaller than the 6 micrometer. Okay, and then for transistors, so it's not easy to count number of zeros in this number. Is actually the number of transistors is the 5.7 billion. And then the first CPU includes the 4.5K, the kilo transistors, but modern CPUs modern CPU includes billions of transistors. The billion is 10억 in Korean, right? Then number of cores is 18 cores because this is the server architecture. So we can just compare the number of transistors between old generation CPU and modern generation CPU. Okay, so 4.5K versus 5.7 billion. So what I want to say is that the modern is that systems are very, 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 very complex. Very complex systems. modern digital systems are very, very complex systems. And then modern chips, a modern single chip includes many transistors. Then question is how we can build these complex systems. No, so some joke is that Intel hires aliens, so they build very complex CPU. They can build very complex CPU. But so recently, Samsung and then some other companies are also manufacturing very complex chips, right? So nowadays we can make very complex digital systems compared to the about 60 years old. No, it's the 50 years old ago. Compared to 50 years ago, we can build very complex design. Then what is the start point? Even though our computer system, so actually this is the CPU chip or CPU chip, and then we know our computer systems are composed of many components, including CPUs. So our computer systems include the memories and I/O devices. Like also our computer systems include storage devices such as SSDs or hard disk drives, and many also our computer systems includes the displays. So just a single CPU includes many transistors. So actually, this means that the CPUs are also very complex digital systems. Then, how can we build these complex systems? This based on the fundamentals, the fundamental concepts of digital logic design. So it starts from the basic digital logic design, which you will learn in this course, right? Okay. So people are mentioning about the digital logic design. So I will mention about the Moore's law. So Moore's law is the very important law in the semiconductor industry. The Moore's law is the very famous law in CPU, actually in the CPU industry. So Moore's law mentions the number of transistors will double every 2 years. So you can find will double every 2 years. So you can think about just the number of transistors double every 2 years. And that is the result of the Moore's law is this CPU. The Moore's law from around the 1970. So you can find the number of transistors was the 4.5K. But as Moore's law continues now, so number of transistors have become 5 billion. So just the Moore's law just mentioned, the number of transistors will double every 2 years. You can think, this is very simple, and then this is not a big deal, but it's very big deal, right? You can find, the modern processor includes the billions of transistors. Is it because every 2 years, the number of transistors increased exponentially? It's a very huge increase in the real world, right? So this graph shows the transistor count. The y-axis is the number of transistors in a single CPU chip, and the x-axis is the years. So And then, as you can see, this is the log scale. The y-axis is the log scale. So which means that, and then you can find this graph, the many bytes in this graph. So this line is a linear line. Okay. So what does that mean? So y-axis is the log scale, which means the number of transistors have increased exponentially. It's a huge increase. Okay. So that's why the computer systems, well, the computer science or computer engineering have changed it very quickly. Okay. Actually, you can find new technologies, also you can find a new concept in computer engineering compared to the 10 years ago or 5 years ago. Okay. So, which means the technology in computer science or engineering have changed very, very quickly. Okay, then what does that mean? Why Moore's law? So why did I mention Moore's law in the computer systems or CPU design? So I said digital design can be easy. So it's easier than the analog systems because the analog systems handle the real analog signals. And then, as I mentioned, the analog signals include the many different values. And then these values are changed continuously. But our digital systems handle only just 0 and 1, zeros and ones. So it's easy. But if we just see the product of digital devices or some digital system, then we can find that digital systems are extremely complex. As I mentioned, a single CPU chip includes the billions of transistors. So which means that these CPUs are also very complex systems. So as I mentioned, so in this slide, you can find a single CPU chip includes the billions of transistors. So as also a single CPU chip, which means that a single CPU chip includes the billions of logic gates. Okay. So in this class, we will learn about the logic gates. Okay. So which means even though the modern digital systems are very complex systems, but building digital systems can start from logic gate. Okay. And then actually it starts from understanding logic gate, some technology and then concept that is the design. We can complex systems. So, which does not mean we can build these complex chips only one or two people. So which means that only one engineer cannot build these complex systems. Actually, the Intel also many engineers are working in Intel, and then really these complex these large CPUs are designed by many engineers. But so actually, we will learn about some concepts of the digital design in this class. But we can build these complex systems from the very small part called the logic gate. And then we can integrate these logic gate, and then we can build the simple digital component. And then by integrating these digital component, then we can build some more complex. And by combining these units, and we can build the complex systems. Okay. Then we will discuss the art of managing complexity. So it means that how we can manage these complex digital systems. Okay. So these are some fundamental concepts of designing these systems. You can find the abstraction and discipline, and then 3 Ys like hierarchy, modularity, and regularity. So as I mentioned, so modern digital systems are very complex, and then it's very big. Actually, one person cannot handle these complex systems. But based on these concepts, design, and we can actually many engineers can handle these complex digital systems. So we will learn about the abstraction and discipline, and then 3 Ys of the digital design in today's class. Okay, it looks like this is the intro of the today's class. Okay, so let's think about the abstraction. And what is an abstraction? So if you read a paper, so like a research paper, then you can find that each paper has abstraction section. And what is an abstraction? So in Korean, the terminology abstraction is called choro, right? But the meaning of abstraction is kind of summary, right? If we read an abstraction section of a research paper, and we can briefly understand the flow, the main idea, and then the flow of an entire paper. That is the meaning of abstraction in real world. Then, what is an abstraction in computer systems or digital systems? So these are the analogy of abstraction. So like so this is the drive. So she is a driver, and then the analogy is the car system, and then this is a vending machine. So I believe some of you have already have driving licenses. So if we have a driving license, then we can drive a car. Right. But which knowledge is required? So which knowledge is required for driving a car? So we can change the direction of a car using a handle, and then if we push on acceleration pedal, then speed is increased. And then if we push the brake pedal, we can make our car. That is our knowledge about driving a car. So it means that using this knowledge, then we can drive. But you know, a car is a very complex system, right? A single car includes also a very complex engines. Also, a single car includes the very complex systems such as the accelerating systems, fuel providing systems, and brake systems. Right. Inside of a car system is a very complex system. Without knowing its knowledge about the system, we can write a car. Okay, vending machine is the same. So this is a customer, and then if we just push a button, buttons of vending machine, then we can purchase product from a vending machine. But inside of a vending machine, the vending machine includes the control systems, like also the vending machine also need to detect the pushing of push of button. Also, the vending machine also controls some product providing system. There are also some mechanical systems inside the vending machine. But in order to use a vending machine, we don't need to know about the detailed mechanism of a vending machine. So I explained the concept of abstraction using the analysis of a car and a vending machine. I said we don't need to understand the detailed mechanism of inside of a system. Also, we don't need to know the difficult concepts or knowledge inside of a system. If we want, even if we want to use complex system, don't need to understand everything. So difficult concepts inside of a system. This is called abstraction. So why abstraction related to systems? So this is the definition of abstraction. The hiding details when they aren't important. Actually, we don't need to understand how cars work for driving. Okay? We don't need to understand the detailed mechanism of a car system. It's the same for digital systems. I mentioned that the digital systems are very complex systems. Okay. A digital system is a very complex system, but we don't need to understand the details of digital systems. So this is the same figure I showed in the class. So our computer systems are composed of many layers, but we just focus on each layer for research or for study. But in the junior or sophomore years, that we just every aspect of the computer system, but in the sorry about that. Freshman or sophomore year, and we just handled some basic concept of each layer. But in a junior or senior years, that we just focus on the specific layer of the computer system. So which means if you are interested in operating system, then you can take the operating system course, and then also you can take some related courses like the system programming or some other system software courses in the junior or senior years. So, but if we just focus on the operating system, then you can the knowledge of the architecture, because the architecture is the first below the operating system layer. You don't need to understand the detailed mechanism or detailed knowledge or detailed systems of architecture. You can just focus on a certain layer of a system. So what is the benefit? Because a system is very complex, but we just divide this system into many layers, then we just focus on a certain layer of a system. So for example, software engineers just write a code, but they do not consider about some detailed mechanism of resource sharing or resource management and hardware management of a computer system. That is the role of operating system. So actually, the software engineers write the code considering our system has infinite cores and then very large memories, and then very infinite resources. It's not true, but they do not consider about the detailed mechanism of underneath layers. So they can focus on their own layer because some details can be hidden. That is the concept of abstraction. Okay. Then, so this is a benefit of abstraction. And what is the disadvantage? Disadvantage of abstraction. It's not easy. It's not easy optimizing entire system, right? Because we are just people just focusing on people just focus on a certain layer only, then it is actually this layer and this layer are separated each other, then they just focus on the operations in this layer. But for the global, in order to optimize the system globally, then we need to also focus on every aspect of this system. But because we just focus on only one layer of the system, and it's not easy for optimizing globally. So that is the disadvantage of abstraction. Okay? But we require the concept of abstraction because we are handling very complex systems. So that is the art of handling complex systems. So this is the abstraction. So this is another example of an abstraction. So as you can see, this is the dipole of Intel CPUs. So we can observe many transistors. Then can you understand how the chips are this CPU is designed? So if we just see this photo, we can just observe, this single CPU includes many transistors, and that is the knowledge or knowledge we can get from this photo. But this is some more detailed abstraction level. So on this photo, you can find, this is the CPU core, and then this is the battery pack, and then this is the network, this is a GPU. Okay. So by adding some information, then we can just show the detailed abstraction level. Okay, so if the detailed abstraction is provided, then we can understand more about the system. Okay? And then desuffling. So the meaning of discipline is intentionally restrict design choices. So this is an example of digital discipline. So as I mentioned, the real signal is the analog signal, and the analog signal has many values, many continuous values, but this analog signal can be represented using digital signal like this. So as you can see, these signals can be represented using just value 1, and then actually this period, then we can represent the signal in value 0. So what does that mean? We just reduce some possible values of real signals. Why? We just promise so we can represent this analog signal like this signal using 1 and zeros, 1 and zeros, 1 and zeros, something like that. So as you can see, the signal is much simpler than the analog signal. And we actually, and then because we reduce the possible cases for representing signal, then we can simplify the signals or data we need to handle in our system. Okay, this is the discipline. So we can intentionally restrict design choices, not to simplify design process of our system. Okay, that is the discipline. And then 3 Ys, like hierarchy, priority, regularity. And then these are the definitions of 3 Ys, a hierarchy. A system divided into modules and sub-modules. So hierarchy means the 계층구조 in Korean, or some it's not a good meaning in real world, because hierarchy means like the ruler and the subordinate in a social systems. But this kind of system, hierarchy means this system can be divided into modules, many modules, and then also inside of a module, and then this module can be also divided into the many sub-modules. This is the meaning of hierarchy in data systems. And then modularity. Modularity means that we can define a certain block or certain unit using functions of this unit and interface. Interface means that inputs and output signals of this module. So, for example, it looks like the black box, and then this is the function. And then if input signal or input data is provided into this module, and then output is generated. And then this concept is called modularity. So we can design a module like this. And then when the module is designed, we need to define a function of a module and input signals or input data, output signals. So we can define a certain unit or a certain module of a digital system like this. Okay. And then regularity. So regularity means that we can each module or some digital modules in digital system can follow a certain unified policies. Okay. And then we can also use the same modules to build a complex digital system. For example, we can copy and paste our design module to build a very complex system. So I will show example. So let's see the hierarchy concept of a digital system. So this figure shows a sky-like topology. So it's also the server architecture. So what can you observe in this figure? So, so actually, if we see the dipole of the CPU, then you can the dipole looks like this. But inside of this CPU, this is the architecture of the Intel Skylake topology. So actually, so which means that the Intel server CPU includes the cores find here, so core. And then also you can find the interfaces here, like UPI and PCIe, and then some other interfaces. Also, you can find the memory controllers, and then DDR channels, DDR interfaces. So, inside of a single chip, it's a single chip. So, single chip is a kind of a module. Then you can find many sub modules like the core, and then some interfaces, memory controllers, and then memory channels. So these are sub modules. Also, inside of each core, you can find many modules. This is the architecture of the. So you can find the yellowish here, here, each color, greenish color. So you can find here. So the violet color, as you can find the violet color here. So actually, the figure shows the more detailed architecture of a single core. So you can find many modules. Okay, so I think you can understand because you do not take a computer architecture yet, but these rectangles represent blocks or modules. So which means that inside of a core module, there are many sub-modules. So this is the hierarchical design. So it's like it looks like this. So so it's a single core. We can find many sub-modules here. So we can hierarchically build our complex system like this. So it's an example. So inside of a core, there are many modules here. And then modularity. So this is an example of modularity. It's a register file. So if you see this figure, you can find that, oh, this is just a rectangle, right? It's just a block or module called registers. And what can you observe? We can observe the input port. Okay. Then also this is the width. Okay. We learn about the bits. Flat. Number of bits. And then also we can find output. So these are interfaces. So this register file, so register file module, this is our module of the system, receives these input signals with register 1, with register 2. These are output ports, bit data 1 and bit data 2. Okay, and then also I write the functions of register file. So as I mentioned, it looks like this is the function, and then inputs and then outputs. So we can design a module of the digital system, of module of digital system. Yes. We can define the required functions for each module, and then we can define required interfaces, inputs and outputs of module. Okay. This is an example. This is an example of modularity. Okay. We can design a simple module, and then we can combine these modules like Lego blocks. Okay. This is, so we can build a very, very complex system. Also, finally, regularity. So it's the same figure. So in this figure, we can find a same core. So what does that mean? You can just copy and paste a single chip in many cores, and then many cores are connected via interconnector. Well, so we can use the same single core to build a large chip. Okay, we can just copy and paste the same module to build a large module. So this is the regularity. Okay, so if we just follow the concept of regularity, we can just copy and paste our design to build complex system. Okay, it's very important because the regular design is very important. Okay, so we can just reduce the effort for building complex systems. Okay, so this the abstraction is also this is the signal. Okay, so actually I said the system handles the digital signals. Digital signals are also kind of abstraction because the complex analog signals can be represented using a simpler digital signals. So I will explain about this abstraction in the later classes. Okay. So in this class, I explain about actually this kind of introductory class also for this course, but I hope everyone can understand, everyone can know that this concept of digital design, the abstraction. So actually, the abstraction is very important for complementary students. So we also use many abstractions in the software design, and then discipline, and then 3 Ys. So using this concept, and we can have the very complex digital system design. Okay, so I will stop here, and then please read the chapter 1.1, 1.2, and 1.3 of the textbook. Okay. Okay. Any questions? Thank you for your attention, and see you in the next class. Bye.